Hello to all of you and welcome back to my SP2 channel. This is going to be the last video of this chapter. We're looking at the last property, which is electron affinity, its trends in our periodic table, and just like always, a practice for you. Okay, so starting by the concept and the definition of electron affinity. So the electron affinity is actually referring to the amount of energy changed. I'm going to say that one more time. The energy changed when we are adding an electron to a neutral atom. And again, it has to be in a gas phase, right? And we are forming a negatively charged ion. It is a very important property because we can understand the reactivity and the chemical behavior of our elements and mostly for the nonmetals. Okay. So for example, I can have something like chlorine. When you add an electron to chlorine, you turn that to chloride. This amount of energy, the EA, right, is our electron affinity, which is actually an exothermic process. That's a negative energy because we are releasing energy, okay? You make something that is more stable. So chloride is more stable than chlorine. But if you do that for something like beryllium, right, you're adding an electron to beryllium, then that will be a positive electron affinity, which means that we have endothermic process. So I need to add energy and convince beryllium to accept this electron, right? That's what I mean by the energy change. It could be positive, it could be negative, depending on the stability and the reactivity of our starting material, right? Excellent. Okay, so as we said, the electron affinity is an important concept in predicting the stability and the reactivity of our anions, right? Especially when they are trying to form ionic bonds. It also helps us to understand why there are certain elements that are super happy and very ready to gain electrons, but that is not the case of many other elements, okay? Now, think about your ionization energy that we had it in our previous lecture, right? So for ionization energy, we were looking at the energy required, always required, when you are removing an electron from your reactant, right, from your species. But for the electron affinity, it's exactly the opposite process. You're adding an electron, right, in terms of the reaction, it's exactly the opposite reaction. The electron must be on the reactant side. But in terms of the energy, it goes by the energy change because it could be positive or it could be negative energy, right? Depending on the stability of our reactant, okay? Now we're going to be looking at the periodic trends in our electron affinity. So if you are moving across a period, EA, your electron affinity, generally becomes more negative, which is indicative of having a stronger attraction to gain electrons, right? This is what we see as we move from the left to the right side. And the main reason is we are having a stronger effective nuclear charge, which makes it easier for the atoms to attract the additional electrons, right? So this is what we call high electron affinity, or we expect to get, negative value. If you are moving down in a column, the EA generally becomes less negative, less exothermic, or even sometimes more positive, right? More endothermic. And that is mainly because the added electron is farther from the nucleus, right? In a larger atoms, right? As you go down, resulting in a weaker attraction. Okay. So here is a couple of examples for you on the table. Bear with me. So here, for example, for the lithium row, right, as you can see, we are getting larger and larger in the value, like more negative, right? When you're looking at, let's say, going down the column, sometimes we have, positive, sometimes we have a slightly negative, right? But the overall trend is kind of understandable, right? But watch out that we always have both positive and negative trend for our electron affinity. Okay, so that brings us to our practice. So consider the first ionization energy of neon and the electron affinity for fluorine, okay? And we try to write the equations for both of these, and we actually trying to put the electron configuration to understand the energy change, okay? There are going to be two opposite signs for these two energies. We'll try to put them in a proper sign as well, okay? So for my neon, starting by neon, It must be in a gas phase, right? So I always have the gas, and I'm looking for the ionization energy. So I'm going to add energy to remove an electron from neon, and you make that as a positive neon, right? Plus an electron. Okay, I'm going to put the electron affinity for fluorine on the right side. So fluorine is gaining an electron, right? That's my electron affinity, and it's going to become fluoride. Okay, cool. Now, if you look at your electron configuration for neon, I'm going to go by 1s2, right? 2s2, and then I have 2p6. If you try to remove an electron from a closed shell, that's not going to be easy, right? And that's why I need to have a positive energy here. So I'm going to go to 1s2, 2s2, and now we have 2p5 because we lost an electron. And that must be a positive value, right? So IE must be positive. Now for fluorine, you start from 1s2, 2s2, and then 2p5, right? And then you add an electron to that, and you're going to make it as a noble gas configuration, right? Which is quite a stable. So because you're making more a stabilized product, we're going to have releasing of the energy. So your electron affinity here must be a negative value, right? For the first one, I can say this is an endothermic process, right? Endothermic. But for my ionization, or sorry, for my electron affinity is going to be an exothermic process. Okay, I hope that makes sense to you. Cool, cool. Thank you very much for watching all of these videos. We're done with this chapter. I'll see you soon on the next chapter. Take care and bye-bye for now.